Good afternoon, everyone. My name is Calina. I'm a second-year PhD student at the University of Birmingham, and I work under the supervision of Dr. Hong Duong. And today I will present you the paper, Cost Optimization of Hybrid Institutional Incentives for Promoting Cooperation in Finite Populations. Say that 5 times fast. The work is joined with my supervisor, Dr. Hong Duong, and our collaborator, Dr. Tan Han. And before you decide to leave and click out of Zoom, I will give you a short summary of what's going on. So basically, we've got a finite population of individuals, and we've got an external decision maker in the United Nations or NATO that has got the budget to intervene in our population in order to promote cooperation via reward and punishment. That is basically the main idea of the paper. Sorry, I can't. Oh, there we go. And the talk is going to be structured as follows. I will give you a motivating example. I will introduce a few bits and bobs. Then I will give you the model as well as present the cooperation dilemmas. I will present you our results, and then I will give you a quick summary and some future research paths. Right, the motivating example is the coolest game in town, the prisoner's dilemma, which I'm sure you all have heard about, but please indulge me in walking through it once again. We've got 2 thieves. They get caught cheating and stealing, and they are brought in for questioning by the police. They've got the following options. I hope you can see my mouse. If both of them cooperate with the police, they get 3 years in jail. If one of them cooperates and the other person defects, the cooperator walks freely whilst the other person goes to prison for 5 years. And if they both defect, i.e. they choose to cooperate with one another as opposed to the police, they each go to prison for 1 year. Now, the actual Nash equilibrium of the game, so the strategy from which players are not motivated to change, is this one here, 3-3. But obviously, if we're just looking at the payoff matrix, there's another option here that would give a lower payoff, because in this case, since we're talking about jail time, our thieves would prefer for that payoff to be minimized. And that is defect, i.e. cooperating with each other. And this is an example of when cooperation between players is important, as it would give a smaller, basically, time in jail. And this is why we're interested in promoting cooperation, well, one of the reasons anyways. What we know is that Darwinian natural selection involves survival of the fittest. We know there's plenty of competition between individuals and between self-regarding populations. However, we also know that cooperation is essential for populations to develop. And my favorite example to give here is, well, how humans come into existence. We start from being 2 cells, and those cells proliferate in order to create organs, and then systems of organs, and then, well, tiny humans, and then humans. So that's all possible because the cells have decided to cooperate. Because cooperation is so important, we would like to promote it within self-regarding populations. And there's many methods to do so. Direct reciprocity, A helps B, B helps A. Indirect reciprocity, A helps B, then C has witnessed that A has been helpful and C helps A. Network reciprocity, one helps people in the network group. Kin selection, helping people one's related to. And institutional incentives, among which reward and punishment, which are the focus of our work. We're not only interested in promoting cooperation by institutional incentives, we're also interested in making it cost efficient. Just to remind you, we want to promote cooperation by cost-effective interference. We've got an external decision maker like the United Nations or NATO that interferes in populations in order to achieve a desirable outcome. There's obviously quite a big ethical concern here because, well, it's desirable according to whom and for whom, and like the ethics behind needs to be properly discussed. I personally am a mathematician, so this is not the focus of this talk, but that's something to be thought about. Apart from that, what we know about this type of institutional incentives is that they enable large-scale cooperation. But they're, however, costly, both in human resources and in equipment. So naturally, we're interested in minimizing the cost whilst also ensuring a sufficient level of cooperation. What the sufficient level actually means depends on the circumstance. So for example, if we are trying to pass a referendum, that might be 51%, or in other cases, it could be as high as 90%. Again, we're just denoting in our paper, we're just denoting it by little omega. And in the algorithm, it can take any value depending on what one wants to achieve. Moving on to the model, we've got a well-mixed finite population of n self-regarding individuals, and they interact with the neighbors using cooperation dilemmas. Just as a reminder, a cooperation dilemma is a type of game in which individual rationality leads to collective irrationality. And I will be presenting the cooperation dilemmas we looked at further on in the presentation. Our individuals can either be a cooperator or a defector, and we are indeed assuming a small mutation rate. The strategy update is based on imitation dynamics, also known as Fermi's rule, which is this probability over here. So the probability of player X changing strategy with the strategy of player Y is given by this formula over here. And the most important quantities here are beta, the strength of selection, which shows how likely players are to imitate each other, and the difference in fitnesses, F sub Y and F sub X. So what happens here? The players look at one another, and if they see someone else is doing better than them, then they might decide to change strategy. And that very much reflects how humans behave in general. And again, one of my favorite examples to give here is how everyone nowadays is becoming an influencer because they've seen how well influencers are doing financially, and not only that. Again, the strength of selection beta is really important because if players are not likely to copy each other, then any change in strategy would be due to noise as opposed to the actual incentives. But the larger the strength of selection is, the more likely our institutional incentives are to succeed. Onto the investment policy, we model this on a Markov chain starting at state 0 and ending at state n. State 0 and state n are absorbing, so we're basically looking at what happens between state 1 and state n minus 1. And the index of the state just means how many cooperators there are in the population. So if we are at state k, like we are in the investment policy example, that means that we've got k cooperators in our population. Our lovely external institution gives us theta k amount of money, and that is times by the minimum of the number of cooperators divided by A and the number of defectors divided by B. A and B are just numbers representing how efficient our reward and punishment are respectively. And the idea here is if we've got a very large number of cooperators in the population, it would make no sense for the institution to further use the money to reward cooperators. It would make more sense to use it to punish defectors in order to lower the number. Equally, if we've got a lot of defectors in the population, it wouldn't make sense to use the money to punish the defectors. It would make more sense to encourage cooperation by rewarding cooperators. And that is the idea behind the investment policy scheme. The maths formulation, we're minimizing across all possible mixed cost functions that ensure our desired level of cooperation denoted here by little omega, and it's between 0 and 1. And obviously, theta is just the cost per capita, and we would like that to be greater than this value over here, theta 0, which was obtained by just putting a constraint on the level of cooperation. Perhaps you're wondering how we're obtaining the mixed cost function. We get that from the matrix of the Markov chain, n sub 1, j and n sub n minus 1, j are just probabilities of going from state 1 to state j and from state n minus 1 to state j. And after we've obtained our function, we will be doing analysis on it, as you'll see in the results section. Something that's very important and that makes the analysis tractable is the fact that the payoff difference between cooperators and defectors at any state k of the Markov chain does not depend on the state of the Markov chain. That's a very important fact that helped us a lot in our analysis. Now, I mentioned that we looked at two cooperation dilemmas. We looked at the donation game and the public goods game. In this slide, I will talk you through what these two are and why they make sense. So basically, the donation game If you look at it and think it looks like the prisoner's dilemma, well done. It is kind of the prisoner's dilemma. It's a generalized version of the prisoner's dilemma. And as you can see here, if both our players cooperate, then they receive a benefit after having paid a cost. If one defects and the other one cooperates, the defector gets the entire benefit without paying the cost, whilst the cooperator just pays the cost. And if they both defect, they get nothing. The issue here is that from a game theory point of view, in which a player is always rational and is always trying to maximize the payoff, obviously the choice of strategy would be always to defect, because you'd always get the benefit without actually paying the cost. And you'll see it's kind of the same idea in the public goods game, which I'll present in a second. But the issue with this type of behavior is that, for instance, with healthcare that is shared by everyone, only some people pay, but everyone benefit. And if people decide not to pay anymore, then that would obviously collapse. And it's the same in the education system and these types of institutions. The public goods game, very similar idea. We've got, in this picture that I've got on the slides, we've got 4 players, each start with $20, and each have got the choice of secretly putting money away in a common pot. The secret part is really important, as people do tend to behave differently when they're being observed. Once the money is in the common pot, it gets multiplied by a factor. Here is that number is 1.2. And then the money is distributed equally amongst all the players, regardless of whether they were defectors or cooperators. And as you can see at the end, our cooperators ended up with less money, whilst our defector ended up with more money. Again, from a game theory point of view, well done, player 4. You've maximized your payoff, but from a social point of view, that might not always be good. And this is why we would like to encourage cooperation. On to the results. I'm not going to tell you that we've invented the wheel. People have looked at institutional incentives before, have even mixed reward and punishment before, but people haven't taken into account the idea of cost efficiency, and moreover, the idea of sustaining a specific level of cooperation. This number over here in the middle of the slide is a quantity that appeared all throughout the analysis, and I've decided to put it on the first slide so people know what it is. It's a bounded number, so it's got a limit, which I have not given on the slide, but it is in the paper. Our first and main result is the fact that it is always more cost efficient to use the mixed incentive approach as opposed to a separate one, either using reward or punishment. And in certain cases, if it's really cheap to reward, then our mixed cost function will turn into reward. And equally, if it's really cheap to punish, then our mixed cost function will turn into punishment. And that's the first result. We've also run simulations. So here you can see our cost function and our cost per capita, our mixed cost function and our cost per capita. And we've compared the cost for mixed incentives in blue with only reward in orange and only punishment in green. This is for the donation game with various strengths of selection and with the benefit of 2 and the cost of 1, which is kind of standard when describing the donation game. And as you can see, it is always cheaper to use the mixed incentive approach. The picture looks similar for the public goods game, so I didn't include it in here. We've also done analysis on the mixed cost function, and we firstly looked at the neutral drift limit. So basically what happens when our strengths of selection, which, just to remind you, was when players weren't very likely to copy each other, and it's this limit over here. Again, our quantity H and AB shows up here as well. And then we wondered what happens when it's the opposite happens, when our strengths of selection is quite large. So players are very likely to copy each other. And we've got this thing over here, and have no fear, we actually have simulations to show what's going on and to show that the limits actually work if you don't trust analysis. On the left-hand side, we've got the donation game, whilst on the right-hand side, we've got the public goods game with these values over here, which are quite standard for both games. And as you can see, our mixed cost function is stuck between the 2 limits. The red line is the neutral drift limit, whilst the green line is the strong selection limit. Excuse me. we also, since we're assuming a finite population, but we're also wondering what happens when our number of people in the population approaches infinity, so it's very large, and we obtain these two limits over here, which please note that they do depend on the game. Previously, our limits didn't depend on the game. And again, just to prove you that we're doing something right, we've got our lovely simulations, left donation game, right public goods game with the usual parameters. And as you can see, in both cases, our mixed cost function follows perfectly the limit. We've also bounded the mixed cost function between two values, and I'm not going to bore you too much with this. And we've also observed a very interesting phenomenon. We observed a phase transition in the function. Sorry. Yes, I'm almost done. We've got the phase transition phenomenon, which, since we're running out of time, I will just skip straight to the pictures. So basically, when the strength of selection is quite low, our function is nice and increasing, and our cost per capita just equals theta 0. However, when our strength of selection becomes higher, then our mixed cost function is increasing, then decreases, and then increases again. So we need to choose between two values, which we denoted in the algorithm, well, our usual theta 0 and another value, theta 2. And the behavior of the cost function of the phase transition is quite interesting, and it would be very nice to have a feel for why that is happening. And in the algorithm, since I'm running out of time, just quickly, the algorithm in the algorithm, one just puts in the parameters for the game, chooses the game, puts the parameters in, and then obtains the optimal cost per capita that will minimize cost whilst ensuring a sufficient level of cooperation. Just a quick summary. We've presented a cost-effective interference mechanism for promoting cooperation. We've shown you the rigorous analysis of our cost function, as well as our lovely asymptotic limits, the neutral drift limit, strong selection limit, infinite population limit, as well as the very nice phase transition that happens with our function. In the future, we would like to see what happens for any mutation rate, since we only assumed a small mutation rate. We would like to see what happens in more complex games where the payoff difference depends on the state of the Markov chain, as in this one, it didn't depend on that. Spoiler alert, the analysis might become intractable, but we will see. And finally, we would like to see what happens in structured populations. So perhaps our players would interact on a graph as opposed to everyone interacting with everyone, as that's not very realistic. But this is all for me. Thank you very much for listening. And I'm not sure if we've got time for questions, but thank you very much.